An explosion of ocean life some 471 million years ago was not sparked by a meteorite bombardment of Earth, said a study Tuesday that challenges a leading theory without offering an alternative explanation for what is known as the Great Ordovician Biodiversification event. Researchers from Sweden and Denmark said the creature expansion started some 2 million years before the space rock bombardment. This was based on fresh dating of crystals from meteorite-bearing sediments in Sweden. The study shows that the two phenomena were unrelated, researchers wrote in the journal Nature Communications. For study co-author Anders Lindskog of Lund University in Sweden, the data showed there is no measurable extraterrestrial influence on biodiversity in Earth's oceans. The GOB, which vastly expanded marine life diversity, kicked off about 70 million years after the first explosion of life on Earth during the preceding Cambrian period, some 540 million years ago. Some scientists contend that the Ordovician event was sparked by a collision of objects in the asteroid belt between Mars and Jupiter, raining debris down on our planet. Such a bombardment may have changed the environment just enough to stimulate diversification of existing life, the theory goes. The question of what caused it remains open, but Lindskog speculated it was likely a combination of events and processes. It is reasonable that the very high sea levels that prevailed during the Ordovician simply gave more space for life to thrive, he told AFP. Combined with the presence of many small continents and beneficial climate change, we have a pretty nice recipe for biodiversification, he said by email. It comes as scientists reconstructed the ancient meteorites that fell to Earth after a cataclysmic collision in space 466 million years ago. The study has revealed a shift in the types of meteorites seen today versus those in the past, with many that are rare now found to be common millions of years ago. These findings shake up the conventional belief that the solar system has been stable over the last 500 million years. In the study, published to Nature Astronomy, researchers investigated the difference in meteorites before and after the massive collision 466 million years ago. When something slammed into an asteroid and broke it apart, we found out the meteorite flux, the variety of meteorites falling to Earth, was very different from what we see today, said lead author Philip Heck of the Field Museum in Chicago. Looking at the kinds of meteorites that have fallen to Earth in the last 100 million years doesn't give you a full picture. It would be like looking outside on a snowy winter day and concluding that every day is snowy, even though it's not snowy in the summer. The collision sent chunks of rocks, meteorites, raining down on Earth, and as this debris is formed from many types of collisions, including those between asteroids, moons, and even planets, they have different compositions, reflecting those of their parent bodies. Much of what is known about the meteorites that fell millions of years ago, however, has long remained a mystery. We knew almost nothing about the meteorite flux to Earth in geological deep time before this study, says co-author Birger Schmitz of Lund University in Sweden. The conventional view is that the solar system has been very stable over the past 500 million years, so it is quite surprising that the meteorite flux at 467 million years ago is so different from the present. To understand more about these ancient events, the researchers analyzed micrometeorites from more than 466 million years ago. These are tiny specks less than 2 millimeters wide. The researchers gathered samples from a now exposed ancient seafloor at Lena River in Russia. Then, they dissolved the micrometeorite containing rocks in acid, leaving behind just microscopic chromite crystals. Chrome spinels, crystals that contain the mineral chromite, remain unchanged even after hundreds of millions of years, explains Heck. Since they were unaltered by time, we could use these spinels to see what the original parent body that produced the micrometeorites was made of. The analysis revealed differences in the chemical makeup between the meteorites and micrometeorites that fell before 466 million years ago and those that fell after. While just 0.45% of meteorites that fall to Earth today are in a class known as primitive achondrites, the researchers found that these made up 34% of the pre-collision samples. They also discovered relics from Vesta, the brightest asteroid visible from Earth. Vesta experienced a collision event more than a billion years ago. The researchers say meteorite delivery from the asteroid belt to the Earth is a little like observing landslides started at different times on a mountainside, said William Botke of the Southwest Research Institute. Today, the rocks reaching the bottom of the mountain might be dominated by a few recent landslides. landslides going back in time. However, older landslides should be much more important. The same is true for asteroid breakup events. Some younger ones dominate the current meteorite flux, while in the past older ones dominated. The researchers say these findings can help to develop a better understanding on the formation and evolution of the basic components of the solar system. Knowing more about the different kinds of meteorites that have fallen over time gives us a better understanding of how the asteroid belt evolved and how different collisions happened, said Heck. Ultimately, we want to study more windows in time, not just the area before and after this collision during the Ordovician period, to deepen our knowledge of how different bodies in solar system formed and interact with each other.